For the first time in modern cosmology, evidence is emerging that the expansion of the universe might not be what we long believed. Celebrated physicist Michio Kaku has been analyzing the latest data from the James Webb Space Telescope, the Dark Energy Spectroscopic Instrument, and the growing enigma known as the Hubble tension. What he's found has prompted an urgent warning, one that could upend our entire view of the cosmos and its future. The most recent observations from JWST, DESI, and ongoing Hubble studies have stirred intense debate among leading cosmologists. The growing body of data suggests that our understanding of the universe's expansion may be fundamentally flawed. As Kaku put it, the textbooks we've relied on for generations might need to be rewritten, and the reasons why are truly astonishing. Right now, cosmology is facing a foundational crisis. Scientists have long used two independent and highly trusted methods to calculate the rate at which the universe is expanding, and shockingly, they're arriving at two very different results. When they examine the early universe, using data from the Planck satellite's view of the cosmic microwave background, they arrive at a figure of 67 kilometers per second per megaparsec. But when they measure local expansion using Cepheid variable, stars and Type Ia supernovae, essentially looking at relatively nearby galaxies, they get a rate closer to 73 or 74 kilometers per second per megaparsec. While the difference might seem small, in cosmology, a discrepancy of 7 units is not just significant, it's a full-blown problem. Both approaches are incredibly precise, and instead of the gap shrinking with better instruments, it's only growing wider. Initially, scientists thought this might be a simple measurement error that would vanish with improved technology, but that hope was shattered in 2024. That year, teams using the James Webb Space Telescope carried out what they described as a triple check of key measurements. Thanks to JWST's powerful infrared capabilities, astronomers could examine Cepheid, stars with an unmatched level of precision. The result? The higher local expansion rate was confirmed with absolute certainty. The Hubble tension was no longer a quirk or mistake. It was a real, persistent feature of our universe. Nobel Prize-winning physicist Adam Rees, who led one of the landmark studies, described the findings with sobering clarity. With errors ruled out, what remains is the possibility that we've misunderstood something fundamental about the cosmos. The growing consensus in the scientific community is that this is no longer just an academic debate. It's a true crisis, one that suggests our current model of the universe is deeply incomplete. But the surprises didn't stop there. JWST soon uncovered something even more baffling: early galaxies that by all logic shouldn't exist. As the telescope peered into the farthest corners of the cosmos, it reached further back in time than any instrument before it. Its mission was to observe the universe as it appeared only a few 100 million years after the Big Bang. What it found completely upended expectations. Scientists anticipated spotting small, newly formed galaxies, rudimentary structures just beginning to take shape. Instead, JWST revealed massive, mature galaxies that looked far too developed for their age. These early galaxies, seen as they were only 300 to 400 million years after the Big Bang, already contained large numbers of stars, heavy elements, and complex structure, traits that should have taken billions of years to emerge. According to the established model of cosmology, the early universe should have experienced a gradual period of development where tiny clumps of matter slowly merged to form galaxies over time. But the galaxies JWST found seemed to skip this entire phase. They had already formed stars at a rapid pace when the universe was just 3% of its current age. These galaxies were anything but primitive. NASA astronomers were astonished. One report described the discovery as introducing an unexpected population of ancient galaxies, findings that electrified the scientific community and raised serious doubts about our models of galaxy formation. By 2023, JWST had detected many more of these early luminous galaxies than any model predicted. The implications were clear. Something about our timeline of the cosmos was off. And if these galaxies are indeed what they appear to be, then nearly everything we believed about the first few 100 million years after the Big Bang could be wrong. In light of this growing chaos, scientists began searching for a single explanation that could account for both the conflicting expansion rates and these impossibly early galaxies. By late 2024, research teams from MIT and the University of Texas proposed a bold new idea. An intense burst of dark energy in the universe's earliest moments might be the missing piece of the puzzle. This early dark energy wasn't the same force we know today. It was a powerful but brief phenomenon occurring within the first 50,000 years after the Big Bang. If such a burst happened, it could have temporarily accelerated the expansion of space itself, reshaping the universe in subtle but profound ways. This short-lived inflationary episode could have effectively shrunk what's known as the sound horizon, the scale used to measure cosmic distances. That would mean our cosmic yardstick is off, which could reconcile the differing Hubble constant values once the calibration is corrected. But the theory goes even further. After this burst of early acceleration ended, the universe would have transitioned into a phase that was slightly older and less dense than we had assumed. That change in conditions might have allowed galaxies to begin forming earlier and more quickly, matching exactly what JWST is observing. Simulations run by the MIT team confirmed that when this early dark energy is factored in, the number and brightness of ancient galaxies seen by JWST can be accurately reproduced. At the same time, the discrepancy in expansion rates disappears. It's a compelling solution, one that links two major cosmological puzzles with a single revision to our understanding of the universe's infancy. But just as this theory began to gain traction, a new wave of data emerged, suggesting something even stranger. Dark energy might be changing again. In April 2024, researchers using DESI, the Dark Energy Spectroscopic Instrument, unveiled results that shook the scientific world. DESI had constructed the most detailed 3D map of the universe to date, charting millions of galaxies across billions of years of cosmic history. What they found contradicted a bedrock assumption that dark energy has been constant over time. For decades, this mysterious force has been treated as a steady, unchanging property, like gravity but working in reverse, pushing the universe apart. But DESI's data tells a different story. Patterns in galaxy distribution didn't quite align with expectations unless dark energy has been slowly weakening. According to the team, the force that's been driving the universe's accelerating expansion may be losing strength. Adam Rees, who helped discover dark energy decades ago, described this as the first meaningful clue about its true nature in 25 years. The implications are enormous. If dark energy is not constant, then the future of the universe may be far more unpredictable than anyone thought. Multiple independent observations are now converging on the same conclusion. Dark energy's grip on the cosmos may be fading. This suggests the expansion of the universe might be starting to shift gears. Over trillions of years, that could mean the acceleration slows, perhaps halts, and maybe even reverses. We could find ourselves in a static universe, or one that's starting to contract. If dark energy eventually reverses direction and becomes attractive, it could trigger a gravitational collapse, a big crunch, reversing the Big Bang in a fiery end. Some scientists now speculate that we might be just one phase in a never-ending cycle, where the universe expands, collapses, and is reborn again and again in a grand cosmic rhythm. Even as scientists debate these deep uncertainties, one thing is becoming clear. We've reached a point where we can measure time itself across the universe with astonishing precision. According to Einstein's theory of relativity, distant events in an expanding universe should appear to unfold in slow motion, a phenomenon called time dilation. For years, detecting this effect proved difficult. Some studies, especially of distant quasars, failed to show the expected slowdown, leading to whispers of a problem with our expansion model. But recent breakthroughs have finally confirmed that time dilation is real and measurable. In 2023, a team led by Geraint Lewis studied quasars from when the universe was just 1 billion years old. Their results showed that time back then ran 5 times slower than today, exactly in line with Einstein's predictions. Similarly, detailed studies of distant supernova using data from the Dark Energy Survey showed clear, precise time dilation in their light curves. These results confirm that the universe's expansion is absolutely real. We're not in a simulation, and the physics we depend on still holds. But because we can now measure time so accurately, we also have a sensitive tool to detect even the slightest changes in the universe's expansion history. WST continues to push these boundaries. It recently confirmed a galaxy just 280 million years after the Big Bang, the earliest cosmic clock ever observed. Yet if time itself is stretching in unpredictable ways, we have to ask, what does that mean for the future of the cosmos?